we're going to look at the concentration of solutions here. So a solution is made up of a solvent and a solute. In aqueous solutions, the solvent is water. Concentration is a way to relate the amount of solute to the amount of solvent. Remember, solute is in the smaller quantity and solvent is in the larger quantity. This ratio is the solution's concentration. Typically, concentration is represented in the following way. So some type of concentration, there's a few different ways that we can calculate it, is a quantity of solute over a quantity of solution. This quantity could be in moles, it could be in mass, it could be a volume. There's a few different ways we can represent the quantity of a solute. The quantity of solution, there's only two. We can either look at the mass of the solution or the volume of the solution. We don't look at moles of solution because there's a couple of different things present when we're talking about a solution. Again, it's a solvent, so typically water, with some compound dissolved within. So when we're trying to calculate moles of that, it would be ridiculous. So when we're looking at volume, it's the volume of the entire solution once we've added our solute. Or it is the mass of the entire solution, so the water and the particles itself. A solution is considered dilute if it has a very few particles per volume, and a solution is considered concentrated if it has many particles per volume. So if we look here, we could draw an example of a concentrated solution. So a concentrated solution has few particles in a smaller amount, in our case, of solution. So I'm gonna try and represent the same number of particles in both. So 1, 2, 3, 4, 5, 6, 7 particles. So if I have this concentrated solution, the way that I can get to a more dilute solution would be by adding solvent. So we can dilute by adding solvent. Okay, so if I add solvent, it's going to have a higher volume, but I haven't added any more particles. So there's still the same number of particles. 1, 2, 3, 4, 5, 6, 7. All right, if I would like to go from a dilute solution to a concentrated solution, in our diagram here, we have to get rid of some of the solvent. So we need to remove solvent. The way that we can do that is evaporating. Another way that we could really do this is if we didn't have the time to wait, we could just add, keep the same volume and add more solute. Okay. We'd have to know how many particles are here though, just so that we could calculate our concentration. So there's three main ways of calculating and representing the concentration of a solution. The first one is the amount concentration, or molarity, molar concentration. There's a few different ways of talking about this exact same concentration. It is the most common way to express concentration. So beyond this course, we typically don't look at any other kinds of concentration. However, they do exist, okay? And I'll try and give you some examples of where they come into play. Amount concentration is the chemical amount, so number of moles of solute dissolved in 1 liter of solvent. The formula is concentration is equal to number of moles over volume. Again, where C is the concentration in moles per liter. Okay, that's its unit. N is the number of moles, obviously mole is its unit, and V is the volume, and it has to be in liters. Okay, so in liters, and then this will always be units of moles per liter. So an example, if 0.186 moles of potassium hydroxide is dissolved in 250 mils of solution, what is the molar concentration of potassium hydroxide? So we have our moles, so that is N, and we also have our volume here. That's the volume of solution. So we can use those two pieces of information, and our formula C is equal to N over V. N was 0.186. Volume was 250 milliliters, which is 0.250 liters. Again, it has to be in liters because our unit will be moles per liter. We don't want moles per milliliter. That's silly. So our final answer here, I got 0.744 moles per liter. Significant digits are going to come into play here. We have 3 in our question in both cases, so we need to keep 3 in our final answer. The second example, if 5.420 grams of sodium chloride is dissolved in 100 milliliters of water, what is the molar concentration of sodium chloride? So in this case, I was given a mass, and I have dissolved it in a 100 milliliters of water. Now this is our volume of solution. I recognize that although if we put 100 milliliters and then add some solid to it, the volume may go up a bit, but we pretend that they are not going to do that. Okay, so again, this should just say a solution to kind of mitigate that thought process. Okay, so we have a mass and a volume. We're looking for concentration, which is C equals N over V. And so we need to find moles. Because we have mass, we can use our molar mass to find moles first. So N is equal to little m over big M is what we're going to do first. So 5.420 grams divided by the molar mass of sodium chloride is 58.44. So we get 0.09274. Just a quick note, you should always carry some extra significant digits in your middle calculations here. So our final answer needs 3 significant digits because of this 100 milliliters. So I'm going to keep 4 at least. I don't want to write out my whole calculator every time. So use your judgment. Okay, so now that we have moles, we can go ahead and calculate our concentration. So C equals N over V. Moles we just calculated. And volume is 100 milliliters, so 0.100 liters. And our final answer with significant digits is 0.927 moles per liter. So this is typically how our calculation is going to go in a lab space. We would weigh something on the scale, so we need to know how much mass we need to get a specific concentration. Because our scales can't measure moles, we're almost always going to have to do like this 2-part series. Now, one thing to note, if you like unit analysis, you can use unit analysis here instead. So we would start with our 5.420 grams. We need to cancel mass, so grams go on the bottom. And usually moles are the first thing we want to find. So we're going to divide this by its molar mass, 8.44. Now grams cancel, we're left with moles. This isn't asking us to calculate anything in a chemical reaction, so we don't have to do any mole ratio. We simply need to keep moles because our final answer is concentration, where units are moles per liter. So I need to keep this. Therefore, I'm just going to put a placeholder 1 on the next fraction. To get per liter, there's nothing currently in the denominator. We've canceled grams here. We need a unit of per liter. So we're going to put 0.100 liters here, and that gives us units of moles per liter. Okay, if we calculate this all out, we get the exact same answer. Now, if you don't know or you don't like what I just did down here with unit analysis, stick with your formulas. Okay, if you liked unit analysis, feel free to go through with that. Parts per million is the second type of concentration we're going to look at here. Parts per million is used for very dilute solutions to give reasonable numbers for very small quantities of solute. Okay, so this would be like on the scale of times 10 to the negative, I don't know, 2, 3, 4 for a molar concentration. So we're going to use a number that is more representative. This method of concentration is often used in environmental chemistry, and sometimes you can find it in medical chemistry as well, so blood chemistry. Parts per million, the formula is C. Now, to distinguish it from molar concentration, we just put a little subscript that says ppm. Okay, there was no subscript on the first one, so we have to subscript everything else. So concentration in parts per million is equal to the mass of the solute divided by the mass of the solution, and these are both in grams, times 10 to the 6. Now, often our solution is given as a volume, okay? So you can also alter these formulas by altering units. So it'll be the exact same calculated concentration, so parts per million still, but the mass of solute is measured in milligrams, and the solution is measured as a volume of solution, and it is specifically in units of liters. Okay, you have to use those units to use this formula. I prefer to use this simplified formula without the 10 to the 6, but it's really up to you. Okay, if you're going to use this formula, make sure both things are in grams, and don't forget to multiply by 10 to the 6. Over here, there is no 10 to the 6. It is taken care of by having altered these units. Now, what you need to know as well is that 1 gram of solution is equal to 1 milliliter of solution. So for instance, if I have 650 milliliters of pond water or something like that, I can say that that 650 milliliters of pond water is equal to 650 grams of pond water. And this is because this holds true for water. Okay, 1 gram of water is equal to 1 milliliter of water. And because most things are in aqueous solution, meaning they're dissolved in water, we can use water's characteristics to define that. So that's how you can get from volume to a mass in this equation. Okay. If you're measuring dissolved oxygen levels in a lake, there are 2.2 milligrams of oxygen measured in 300 milliliters of water. What is the concentration of oxygen in parts per million? So we can do this 2 ways. I'll use both formulas just to show that they both work fine for us. Okay, so let's use our first one. The concentration in parts per million is equal to the mass of solute in grams all over the mass of solution in grams times 10 to the 6. Now, there are 2.2 milligrams. So 2.2 milligrams is equal to 0.0022 grams. We have to divide by 1,000 to get to grams. 300 milliliters of water, using our conversion for water, is equal to 300 grams of water. So let's sub into our equation here. 0.0022 grams divided by 300 grams times 10 to the 6. Note that you should get something with two significant digits. I get 7.3 parts per million. Now, again, if you want to see that with our other formula, just to prove that it works, the concentration in parts per million is equal to the mass of solute in milligrams divided by the volume of solution in liters. So we had 2.2 milligrams in 0.3. Because I need to turn this into liters, so that's 0.300 liters. And once again, we get 7.3 parts per million. So it doesn't matter which formula you use. If one works better for you, go for it. Percent concentration is the last one. There's a percent by volume, or sometimes we say percent by volume. Doesn't matter. It's obviously a volume over a volume. Percent mass, or percent mass by mass, is mass over mass. And percent weight by volume, or mass by volume, is mass over volume. So the formula I've simplified to look like the percent X over Y is equal to, like it says, X over Y, where in concentration, we're always looking at the amount of solute over the amount of solution, okay, times 100% in this case. So if I was given a percent by volume question, that would mean that this is a V over V. Therefore, X is a volume and Y is a volume. Now, volumes would have the same units. So if you're going to work in milliliters, that's fine, or in liters, that's fine. Just make sure both have the same unit. Okay, now if we had an equation where we were given percent by mass or percent by weight, we would have a mass over mass. Therefore, X is a mass and Y is a mass. So we're measuring the mass of solute divided by the mass of solution. Again, these are the same variables, so make sure that you're working within grams or kilograms for both so that units cancel. Now, last but not least, if we have one where we had mass by volume, X will be measured as a mass and Y will be measured as a volume. So the mass of solute divided by the volume of solution looks familiar, but we need to get their units to cancel. Now this is where our 1 gram of water is equal to 1 milliliter of water. So what this says is we're going to measure mass in grams and we're going to measure volume in milliliters, because milliliters is also equal to grams, and therefore we could go ahead and cancel our grams and our units have canceled. Okay, so always make sure that when you are using a mass by volume formula, that your volume is in milliliters. Okay, a solution contains 140 milliliters of pure acetic acid that is added to 500 milliliters of water. What is the percentage by volume concentration of acetic acid? So in this case, we're looking at percent volume by volume. Okay, so percent volume by volume means that we need the volume of solute over the volume of solution times 100%. All right, so acetic acid is our solute because it's present in the smaller quantity. Water will be our solvent. Now, I've said that I've added 140 milliliters to 500 milliliters of water. So if I have my 500 milliliters of water and I add another 140 milliliters of a liquid, technically my solution volume will be closer to 640 milliliters. So because this is volume of solution, not just the volume of solvent, we need to actually put this 640 in here. So our percent volume by volume will be 140 milliliters divided by our 640 milliliters, which is the total volume of our entire solution, times 100%, we get 21.9% volume by volume, we should say, because there's a few different types of percent. Okay, a silver nitrate solution has a volume of 13 milliliters and the solution contains 11 grams of pure silver nitrate. What is the percentage weight by volume concentration of this solution? What is the percentage? Careful, because in your notes, this is ever so slightly different. So add the same words. So what is the percentage weight by volume concentration of silver in this solution? Okay, so we have our percent mass by volume, or weight by volume. So we're looking for the mass of solute over the volume of solution times 100%. So the solution has a volume of 13 mils. The solution contains 11 grams of pure silver. So our percent mass by volume is 11 grams divided by 13 mils. Now remember, 13 milliliters of solution is approximately equal to 13 grams of solution, so our units are going to cancel there. This is still times 100%, and I got 84.6% mass by volume. So again, it looks ever so slightly different than what's in your notes, but you still get the exact same value in the end. From here, there are some mixed concentration practice problems. I'd like you to take a look at these on your own and then go back and double check your work using the answer key in my completed notes online. Okay?